we defined single integrals for functions of one variable, double integrals for functions of two variables, and now we're going to take a look at the idea of defining triple integrals for function of three variables. When we were working with function of two variables, we considered a rectangular region on the xy plane, and we defined that region as R being equal to all the points x, y, such that a was less than or equal to x, which is less than or equal to b, and c was less than or equal to y, which is less than or equal to d. That's how we figured out or signed this region. So we're looking at the idea of basically an AB by CD rectangle. Now we want to extend that exact same idea of a rectangular region in R2 to a region consisting of a box in R3. So for three variables, we'll be thinking of a box such that x, y, and z, such that a is less than or equal to x, which is less than or equal to b, c is less than or equal to y, which is less than or equal to d, and typically we jump to something like r is less than or equal to z, which is less than or equal to s. Now, just as before we took this idea of this rectangle and we broke it down into sub-rectangles, we're going to look at sub-boxes. Where each sub-box, box Bij, K, I can identify as xi minus 1 xi by yj minus 1 yj by zk minus 1 zk. So let's see if I can draw something here. So I'm going to have this box region maybe look something like this. See, S, Y, X, and Z. And then we're going to break this up into these little boxes. So that a box inside, like maybe this guy right here, this particular box, if I pull it out, I'm going to call this box BIJK. So this box by itself is going to look something like this. It's just basically a cube. And it's going to have the dimensions delta y, delta x, and delta z. So the volume of each subbox can be represented as delta y, delta x, delta z. So we can estimate the total volume. Say, now let's make it VT. See, volume of the total is then going to be well approximated by the triple sum. Sum I equals 1 to L. The sum J equals 1 to M. The sum K equals 1 to N of f of x I, j, k. Use an asterisk notation again. Y of I, j, k. And z of I, j, k. Delta v. Remember, this asterisk notation simply means I can pick any point in there. So it's a sample point. I guess we say this is the sample point in box I, j, k. That's supposed to be a j. Now, in the limit, we end up with the definition for a triple integral. So that definition for the triple integral says that the triple integral over a box B is over the B of f of x, y, z dv, which equals the limit as lmn goes to infinity of that triple sum that we just worked with, of course, if the limit exists. Now, fortunately, to help us evaluate this, we have Fubini's theorem for triple integrals. And that gives us a very convenient way to actually integrate triple integrals as being iterated integrals. Now, note here also that if f is continuous, then this triple integral will in fact always exist. And also, since we can pick any point in Bijk, any point in that box as being representative, we can simplify the expression quite a bit if we simply choose xi, yj, zk. So this whole thing here will simplify to look like this. Basically, I just got rid of all these asterisks. And then the idea of Fubini's theorem drops in quite nicely, because what I end up with is this triple integral over b of f of x, y, z dv is equal to the integral, I'm going to say from r to s, integral from c to d, integral from a to b of f of x, y, z, and in the order I wrote this, dx, dy, dz. But as we call the nice thing about Fubini's is that we can do this in any order that we want. We can exchange the order. So there's actually 6 different possible orders that we can choose to integrate this depending on the situation that we're working with.